Well, hi everyone. I want to thank you guys for stopping by to watch this video. This will help us to kind of get finished with chapter 14 in a little bit better way so that we have more time to kind of finish up the rest of the material in the last few weeks of the semester. I'm going to be talking about section 14.8 in our textbook. And my title for this section might be something like this: Customized Change of Coordinates. We've been talking about how sometimes when we're faced with a double integral or a triple integral, it's easiest for us to solve it by changing to a different coordinate system. So of course, what coordinate systems have we looked at so far? We have our usual x, y, z rectangular coordinate system. But then recently we talked about how sometimes if we use either cylindrical coordinates or spherical coordinates, so that would be, for cylindrical, that would be r, theta, and z. For spherical coordinates, it would be rho, phi, and theta. Sometimes, depending on the function that we're integrating and the shape of the region or solid over which we're integrating, cylindrical or spherical coordinates can be quite easy compared to rectangular coordinates for doing integrations. So we have this nice set of alternative coordinate systems that we can use for a lot of problems. However, it turns out that this idea of using a different coordinate system doesn't have to stop here. We don't necessarily have to limit ourselves to just a short list of possibilities. In fact, what we're going to talk about today is the fact that we can sometimes literally customize the change of coordinates that we want to use. Right? And we can choose a change of coordinates that exactly simplifies the problem that we are faced with. So I'm going to show you an example here. I've stated a question over here on this side of the board. It's a double integral over a region. Now look at the region here. This region is kind of like it's a square, but it's tilted. And it's tilted in such a way that if you were to integrate with either variable x or y on the outside, if you think about it, you would have to set up two integrals, right? If you chop your region with vertical slices, well, your lower and upper bounds on the rectangle will change halfway across, right, to a different curve. But if you chop the other way, you actually have the same problem. So this region is not well suited to rectangular coordinates, but it doesn't really have any circle nature to it either. So switching this to polar coordinates really isn't necessarily going to be that useful either. So what we're going to try to do with this problem is customize a change of coordinates that will work well for us. The function that we're integrating here, x minus y over x plus y plus 2, all of that quantity squared. Okay? So how am I going to change my coordinates into a nicer set of coordinates? The way that I can get started on that here in this example is I can write down the equations of the boundary of the region R. This is what I'm going to want to do. So for example, the side of the square that is in the first quadrant here, this would have an equation, if you think about it, which is just x plus y equals 1. Right? So x plus y equals 1. This one right here, if we look at that equation, that one is going to be x minus y equals, what is that going to be actually? Negative 1. Right? So x minus y is equal to negative 1 on that line segment. This one right here, well, that's going to be x plus y equals negative 1. And the one on the bottom right, well, that's going to be x minus y equals 1. Okay? So you can check me on all of those equations. Each one of them is a line. Of course, it has 2 points that we can use to create the equation. Those are the equations of those 4 lines. So when I do a customized change of variables, what I am often going to do is I'm going to try to use some different letters. And typically, for this section, the letters that I'm going to use are going to be U and V. And in the case of a 3-variable problem, I would also use W. Okay? And if you look at the nature of what you have on the left side of each of these 4 boxed equations, you might understand why I want to use the following change of variables. I'm going to let U equal x plus y, and I'm going to let V equal x minus y. The reason is, if I do that, then my 4 boundary curves of R become very simple, right? The top right curve becomes the following. So the boundary curves for our region, if we make that change of variables. Again, why am I choosing U and V like this? It's because of the equations, the 4 equations that I wrote down for the edge of that square. I see the U and the V on the left side. And the boundary curves now just become U equals 1, V equals 1, U equals -1, and V equals -1. Right? If you look at the 4 equations in the boxes there, here's what they become when you convert your integral into U and V variables. So the great thing about that is that your integral can now be set up with U going from -1 to 1 and V going from -1 to 1. You couldn't ask for better limits, right? Just constant numbers for your limits of integration. This is kind of the advantage of this. It's very, very easy to get the limits of integration. We also need to put in what the function is. X minus y, that was V. And x plus y plus 2 is U plus 2. That whole thing is squared. And now the dA. I need to say something about the dA. I'm sure you guys remember that when we changed coordinates earlier in these other examples, we had to sort of pay a price for changing those variables. Do you remember that for cylindrical coordinates, I had to put in an R into the differentials in that integration. So dx dy became r dr d theta. And in spherical coordinates, the change of coordinates price that we had to pay was rho squared sine phi. Okay? It turns out that every change of coordinates requires us to pay some kind of price like that. And I need to explain to you how you figure out, or what is the price that you're supposed to pay for the change of variables that you're doing. So there's a name for this. It's called the Jacobian. And let me write down how you do this, okay? So the price for changing coordinates is called a Jacobian. Okay, and that's the official word for it. And how is it calculated? It's called J. Okay, I'll write it as J. And in the case of a 2-variable function, what you do is you do a little, just like a 2 by 2 determinant. Okay, and I'll explain how it's actually done in a second. But what you're going to do is you're going to take partial derivatives of, let's start with the x variable, with respect to u, and then with respect to v. And then on the second line, y with respect to u, and y with respect to v. And you're just going to do a little 2 by 2 calculation. X sub u, y sub v, minus x sub v, y sub u. This is the expression that you have to calculate. Now, in order to do this, notice that what I have the x and the y being differentiated with respect to u and v. So up here, I have the u and the v written in terms of x and y. And I actually need to get x and y in terms of u and v, right? I have to be able to express x as a function of u and v so that I can take these partials. And the same for y. I have to be able to write y in terms of u and v. This means I'm going to have to spend a minute to actually solve these equations the other way around. I'm going to have to solve for what x is equal to and what y is equal to. Now, if you look at these two equations, if you were to add them together, right, do you see what would happen? You get u plus v on the left side. On the right side, the y's would cancel, and you would just get 2x. So if you solve for x, you're simply going to get 1/2 of u plus v. Okay? And similarly, if we solve for y, we can do that by subtracting the equations. If we subtract these two equations, we're going to get u minus v on the left. And on the right, if I subtract, if I take y and I subtract negative y, I'm going to get 2y. So if I divide the 2 underneath to the right side, this is my new equation. Okay? So this is a step that you need to do in order to write down the Jacobian, which is the price that we have to put into this dA in order to do the integration. Okay? So in our example here, what would this give me? If I take the partial derivative of x with respect to u, I just get 1/2. If I take the partial derivative of y with respect to v, I get negative 1/2. Okay? And then minus, I have to take x sub v, which is 1/2, and then y sub u, which is also 1/2. This is actually going to be a little bit of a problem. It comes out to negative 1/2. It turns out the Jacobian should always be made positive because we're talking about area here. The dA is some differential amount of area. It should not be a negative number. So we're going to take, these absolute value bars are really quite telling. Okay, we're going to take the absolute value of the Jacobian that we came up with, and that's going to give me, in this case, a 1/2. Okay? So there you go. That's what we have to calculate. So if I put that in right here, going back to this integral, if I put that in here, I'm going to get the integral u from -1 to 1, v from -1 to 1, of, I'm going to write this as v squared over u plus 2 squared, and then I'm going to put my 1/2. Actually, the 1/2 is a constant, so I can put that on the bar outside, and then dv and du. Okay? So, let's see if we can actually just finish the integral here and come up with an answer. Okay, so the Jacobian, that is the thing that we have to remember to include. It's the price that we pay for changing variables. Okay? I love how these little Kleenex things, or not Kleenex, little mini towels are magnetized here in this room, so I can just set them on the board wherever I want. Anyway, for this one, I'm going to start with the inside integral, which is v. So I'm going to leave my u integration on the outside. That means I can put the 1 over u plus 2 squared on the outside. And I just have to integrate v squared. Right? Well, that's going to give me 1/3 of v cubed. And v cubed is going to be evaluated from 1 down to -1. Okay, so I take 1 cubed and -1 cubed. That's actually going to give me 2. That 2 is going to cancel that 1/2, and I'm going to be left with 1/3 of the integral of u from -1 to 1 of 1 over u plus 2 squared du. U is kind of a bad choice of variables right now because I want to do a u substitution to do this integral. This is like 1 over blob squared. It's just a -2 power, right? So if I anti-differentiate that, I'm going to get a -1 power, and then divided by a -1, which just includes a minus sign here. And really, the du stays the same when you just replace it with u plus 2, right? The derivative of u plus 2 is just 1. So there's no need to really change anything else about that. You could use a different letter and go through a W substitution or something if you wanted to make sure you understand that step. But this is all we're left with to evaluate. So what we're going to get here is 1/3 minus, so in other words, 1 over 3, and then when I put in the lower limit, I'm going to get -1. And that's actually -2/3 which should come out to 2/9. Okay, so hopefully that makes sense. Notice that if I had not taken the absolute value of my Jacobian, I might have come up with a negative answer, right? Normally there's nothing wrong with a negative answer, except we know here we shouldn't get a negative answer. Look at what you're integrating. It's something squared. The function that you're integrating here is always positive, so of course we would expect our answer to be definitely positive in this case. Okay, well, hopefully that makes sense. It's just a customized change of variables. That's really what we are doing. Okay, let's try one more. See if we can practice one more of these here, and then I'll show you a 3-variable version of this as well. Of course, you can pause and go back if I'm erasing too soon. Just put this thing on pause, and you should be able to watch it again. Let's try this example. Let's evaluate, so this is another example. Let's evaluate the double integral over R of xy dA, okay? Where R is in the first quadrant. It is in the first quadrant, bounded by the following equations. xy equals 1, xy equals 3, y equals x, and y equals 3x. Okay? So let's see if we can do this double integral by changing variables to a customized set of coordinates. Okay? Let me start by trying to draw. This time they didn't give us a picture, so let me draw the picture of the region R here. We're only going to be looking at the first quadrant. Okay? The equation x times y equals 1 should be pretty familiar. It just looks kind of like this. It's just a little bit of a branch of a hyperbola. Okay, so that would be xy equals 1. And then xy equals 3 would be a similar shape, just a little bit farther away from the coordinate axes, right? So something like that. Y equals x, of course, is over here going off at a 45-degree angle. And y equals 3x would be going off maybe something like this. So a little bit steeper line. And here's your region R right here. And you can see that that region is not going to be suitable to xy coordinates. You know, it doesn't matter which order of integration you use, this is not going to be something that's good for x and y. It also has no relationship with circles whatsoever, so polar coordinates is really not going to be a good answer for this. If we try to rewrite this region using polar coordinates, it's not going to be something easy for us to write the equations for or to set up. So I would like to think about the curves that are creating the boundary of this region. These are the 4 curves that we want to focus on. And ask ourselves, can we make a customized choice of variables that will make the new limits of integration when we convert to u and v very, very simple? Well, what I hope that you might notice here is that if I let u equal xy, then my first 2 equations are just going to be u equals 1, u equals 3. Okay? And then similarly over here, it's a little bit, maybe not quite as easy to see what we should do, but what we can do over here is we can let v equal either x over y or y over x. It doesn't really matter which one, because now the first equation here is just going to be v equals 1, and this one is just going to be v equals 3. Right? So this is one of the harder aspects of the customized change of variables. It's just coming up with what is the right set of equations here. It's not necessarily going to be given to you. So you do have to think about that a little bit. But let's try this change of variables and see if it's going to work for us. So I know that my new integral is going to have limits which are just going to be u equals 1, u equals 3, v equals 1, v equals 3. Okay, that's pretty nice. xy right here, that's just going to become u. But then the dA. let's not forget, we have this Jacobian that we have to figure out. To get the Jacobian, I have to spend a minute to figure out how to write x and y, which are the old variables, in terms of the new variables. So here I've written the new variables in terms of the old ones. I need to go the other way around. So this is just a little system of equations we have to solve. So for example, I could take y, which is xv, right? And then what I could do here is take the x right here and replace that with u over y. So actually what will happen is y squared will equal uv. So y is going to be the square root of uv. And it's just positive square root because remember, everything is in the first quadrant here. So everything is positive. So this would be what y is equal to. And then if I want to know what x is equal to, well, x, we can use either of these equations to solve for x, right? So x would be, u divided by y, for example. U divided by y would be, what would that be? Looks like it would just be the square root of u over v. Okay, so something like that. So this would be the coordinates that we could establish, right? Something along those lines. Okay. Well, let's go ahead and work out the Jacobian now for this example. So the Jacobian, don't really need the picture anymore because the new picture will be much simpler when I get to the u and v variables. Okay, so let's do this. Let's go ahead and figure out the j. Okay, so it's going to be, remember, the partial derivatives of x with respect to u and v, and then y with respect to u and v. Okay. So x with respect to u, you have to think a little bit here, the v is a constant right now. So I'm just differentiating the square root of u. That would give me 1 over 2 square root of u, and there's already a square root of v on the bottom. So we would have 1 over 2 times radical uv. Okay. X with respect to v, so if I differentiate with respect to v and I hold the u as a constant, this is really v to the negative 1/2. So that negative 1/2 will get pulled down, and then it will be v to the negative 3/2. So I'll put that as v to the 3/2 here, and we still have the square root of u is just up on top as a constant. Okay? It's a little messier this time than the last example. Let's see, y with respect to u. So I hold the v constant and I differentiate that. I should get 1/2 again. And the radical v is going to stay on top. Just put that on top here. And the radical u ends up on the bottom now. Okay? And then when I do y with respect to v, well, it's going to be basically the same thing with the roles of the u and the v reversed. So this is what we should come up with. Okay? Now we just have to do our little formula. X sub u times y sub v minus x sub v times y sub u, right? So upper left corner times lower right corner. Let's see. I'm going to end up with a 1/4, right? I'm taking this number times this number. The square roots of u cancel, and the square roots of v combine into just v. Okay, so we get that. And then we have minus a negative. I'm going to also put down a 1/4. When I simplify this one, the radical u's cancel again, and I end up with a v on the bottom again. So my Jacobian turns out to be 1 over 2v, right? So that is the answer, and the absolute value of that is 1 over 2v, because v is going to be, remember, v is going to be between 1 and 3. So this is definitely positive, so I don't really have to take the absolute value of anything in order to solve this. Okay, so let me go ahead now and set up my integral. Okay, see if we can finish this off. So if we do this, come back up to this integral, remember that the whole idea was that we would just be integrating u and v from 1 to 3. Okay? And xy was, that was what we had set equal to u, right? So xy is just u, and then the dA is 1 over 2v times dv du. So here's the integration that we have to do. All right, this shouldn't be too bad. So I've got my Jacobian in here. I replaced x times y with u, and I'm ready to integrate. I've got my nice limits of integration. This should be pretty easy. I can pull out the u over 2 while I'm doing the inside integral. On the inside, I'm integrating dv over v. That's just going to give me the ln of v. So that's going to be the ln of 3 minus the ln of 1. But ln of 1 is just 0, by the way. Okay, so I can actually pull out the ln of 3 over 2 and just simply integrate. So that's this constant here. I can just simply integrate u du. It gives me a 1/2 of u squared from 1 to 3. And I think if you just take a minute and work all of that out, you're going to get 2 times the ln of 3. Okay? On this problem, the Jacobian was kind of the hardest part. Just getting the old variables in terms of the new variables and then working out the Jacobian. And that can sometimes be the case. It can sometimes be harder to do the Jacobian than anything else. It just depends. It really just depends on the problem. Okay, let me see. Good, a couple of examples so far. Yeah, pretty happy with that. Now, you can also use this customized change of coordinates on triple integrals. Okay, so you can have a problem where you have x, y, and z. So in that case, your customized variables, usually a good choice would be u, v, and w. Okay. And when you do this change of variables, you're still going to have a Jacobian. And the Jacobian in this case is just, x sub u, x sub v, x sub w, y sub u, y sub v, y sub w, z sub u, z sub v, z sub w. Okay? So it's just a 3 by 3. It's kind of like when we did the cross product, right? You remember the cross product? We would go, this was an I, j, k, and we would have sort of 3 terms. Right, one for each of those coordinates. This Jacobian is like that. You start in the upper left with x sub u, right, and you multiply it by the little 2 by 2 determinant yv, yw, zv, zw, right? You would start with that one. Then remember there's a minus on the middle term. If you remember for the j component of the cross product, you have to put in a minus. And then you just get y sub u, y sub w, z sub u, z sub w. And then finally, you have x sub w times the determinant of y sub u, y sub v, z sub u, z sub v. I hope this is all coming out clearly on the board there. Yeah, so that's what you have. And I think my video is going to stop in just a second. So I'm going to start a second video that has the last part of this. But this is the Jacobian, the price you would have to pay to use a customized change of variables for a triple integral. Okay? We should take a minute and just check that it really works for the spherical coordinates and the cylindrical coordinates that we looked at before for those coordinate systems. So I'm going to actually stop my video and do that on the next video. Okay? So I'll see you guys in just a minute.